Hello there. So for this exercise we got this set V that is defined as the real pairs basically are just tuples that the elements are real numbers. So basically this V is defined on R2. We can say that V is equals to R2. And we have defined here the summation operation that is the usual way to sum vectors is component by component, component-wise summation. But this scalar product, the multiplication by a scalar, is defined in a different way. We only multiply by the first element of the vector and we put a 0 on the second component. If you are interested in this kind of mathematics topics, these are related by with projections. So we project just on the first component and we put a 0 on the second one. So this is how is defined the operation on this vector space, and we need to show that actually this space V satisfies from 1 to the 9 axioms of the vector space. So here we got we have just by defining how is the sum of and the multiplication by scalars, we have already proved two of these actions. So here you can see that this is the usual summation of vectors on R2. So just from that you can say that in here that the summation satisfied the axioms related with the summation, but instead we need to prove them. And here you have that the summation of these two vectors, we have u1, v1 are real numbers, u2 and v2 are real numbers, so this will be again a real number and this will be also a real number, so this is also part of B. That is the meaning of the first axiom, the closeness of the addition operation. And related with the multiplication operation with the scalars, we got that this is a real number, and even though that we got always 0, 0 is also a real number, so therefore this also preserves the structure of the set V. That means that this is also part of B, and therefore it satisfies the sixth axiom. So we have two axioms proved just in the definition of these two operations on the space. So let's keep going. Now we need to prove the commutativity of the summation. So here I'm going to define U as before. U is going to be U1, U2, and V is going to be V1, V2. So the left hand side of this equality is U plus B. It's going to be U1, U2 plus V1, V2. We already see what is the result of this is U1 plus V1, U2 plus V2. Great. Now let's see what happened with the right hand side. So the right hand side is V plus U, and this equals to V1, V2 plus U1, U2. The result of this is V1 plus U1, V2 plus U2. But what happened here is that V and U are real numbers, so they commute. We know that the real numbers commute with respect to the summation. So here this is equals to U1 plus V1, U2 plus V2. That means that these two vectors here are the same, and therefore the commutativity is satisfied. Now let's see what happened with the associativity property. Here the W vector will be defined in a similar way, W1 and W2. So let's see what happened with the left hand side. So U plus V plus W, this is just U1, U2 plus the sum of these two vectors will be V1 plus W1, V2 plus W2. And then we sum these vectors. So we have U1 plus V1 plus W1, V2 plus U2 plus V2 plus w2. And then let's see what happened with the right hand side. So u plus v plus w. The sum of these two vectors is u1 plus v1, u2 plus v2, and plus the w1, w2. And the result of this is u1 plus v1 plus w1, u2 plus v2 plus w2. You can verify that these two vectors are the same, so it satisfies the associativity property. Now let's see what happened with the null vector or the zero vector of this vector space. So in this case, the zero vector is just a tuple with the two components equals to 0. They are real numbers, so therefore this is an element on V. That's the first thing. And then we need to show that it satisfies this property here. So u1, u2 plus 0, 0. This equals to u1 plus 0, u2 plus 0, and this at the end is just u1, u2, which is equals to u. Therefore, it satisfies the fourth axiom, the existence of the zero vector. Now let's see if the fifth axiom is related with the inverse of a vector. That means for every vector on V, there is a unique, this symbol means unique, vector minus u that also lives in V, such that u plus that minus u vector is equals to the zero vector on V. So in this case, we're going to define minus u as minus u1 minus u2, just putting a minus in front of each of the components of the vector. And you can see that this is still a real number and this is still a real number, therefore is part of this space V. Now let's see if it satisfies this property. So u plus minus u is equals to u1 u2 plus minus u1 minus u2, and this is equals to u1 minus u1 u2 minus u2, which return 0 0, and we know that the 0 0 tuple vector is equals to the part is equals to the zero vector. So yeah, we satisfy the fifth axiom. Let's continue. Now we got here k. K is a real number or a scalar, and here we are showing that a scalar can be distributed in a sum of vectors. So k times the sum of these two vectors u and v is equals to k u1 plus v1 and u2 plus v2. And here I'm going to make a remark, and is that remember that in this space V, the scalar, the multiplication by a scalar of a vector is defined as k u1 0. That means that we only multiply by the first component of the vector and the second component becomes 0. So following that rule, we obtain here k times u1 plus v1 and here 0. Then we can distribute k in this parenthesis because they are just real numbers, so real numbers, we can distribute the real numbers. So we got here k u1 plus k v1 0. And then here we can separate this as the sum of two vectors, k u1 0 plus k v1 0. And you can see that this actually corresponds to ku and this kv. We have multiplying k by the first component of b, and here k by the first component of u, so this is equals to ku plus kv. The next is sort of distributivity property of a vector over the scalars. So k plus m in this case act as a one scalar, okay, and use the vector, so we know what is the rule for a scalar product for the scalar multiplication with a vector, and we know that this is k plus m times the vector u1 u2, and this is equal to k plus m u1 0, based on the definition of how is the scalar multiplication defined. Then we know that u1, m, and k, I forgot to mention here, k and m are scalars. So here these three elements here are scalars, so we can distribute u on this parenthesis and we obtain ku plus mu 0. And just as the previous exercise, we can separate this as the sum of two vectors, ku0 plus mu0, and you can see that this part here corresponds to ku and this to mu. Therefore, we obtain that this is equals to ku plus mu as we require. The last action that we need to check for this exercise is this kind of associativity property. So k mu is equals to k mu1 0, because it's this scalar multiplication, and then we multiply again, so we have k mu1 0. And the right hand side of this expression is km acting as a one scalar, there's only one, multiplying this vector u. So we got km multiplying u1 u2, and after multiplication is km u1 0. These two vectors are the same, so this property is also satisfied.